Welcome everyone to this 17th session of Statistical Learning in Practice. As I was just saying, we have a practical, and this is going to be on neural networks. So as usual, I'll give you, some time to sort of formulate your questions, and then I can try to answer them. So there is a note here that says that Windows or Mac may have issues. So I didn't have any. I use Mac, and I didn't have any. But it's true that previous years, some students had issues, and this came both from laptops with Windows or Mac. So in such case, in case you haven't been able to resolve that, I suggest you liaise with the student, with a fellow student, and then afterwards try to somehow have Linux on your computer. And it's a shame because we used to have the CATAM room full of computers with Linux. So that, you didn't have to do anything.
Sorry, can I ask a different question real quick? And because I think we can submit the second example sheet on Moodle yet. Where are we supposed to do that?
I have no idea. So I think there must be a button somewhere where it says something like upload your work. There must be, because I have one that is the reverse of that. Which said, yeah, here's the uploaded stuff. So I'm sure you can ask some fellow students, because a fair bit of them submitted solutions last time. So I'm sure easily half of the people know.
Yeah, so there is one for the first example sheet, but only for that. But okay, I'll look it up. Thank you.
Oh, I see. Okay, well, I didn't activate anything for the first one. So yes, I don't know whether I should be activating anything, but I didn't for the first one. Let's see. So Richard answers something. I submitted it to the ES1 space. I see. Okay. Yeah, so I'm happy for you to do it in the ES1 space. Yeah, that's a bit strange, because I really didn't do anything for the first one. So I thought this would be automated. Yeah, I can drop an email to the undergrad office. So let me, in the meantime, send an email as you're thinking of questions. So if I don't make any announcement, then just upload it to the space of the first example sheet. But it's true that it will be a bit messier. So let's see if they can give me a solution. I mean, I don't mind if you don't submit it by 1 p.m., which I think is the deadline I gave. So given this change, I'm happy for you to upload it a bit after. So we could even say end of business day, so say 5 p.m. British time. Okay, so I'll make an announcement later with this, saying that I'm waiting to see if they can activate it. So, and if they haven't by the end of the business day, then just feel free to do it on the first example sheet space. Thank you. All right. Any questions about the practical?
I had a question. Oh, sorry, you go first.
Thanks. When we evaluate the model, we get a loss and an accuracy score. So we have a loss and a metric. And I was wondering, because I guess the loss is being used for the training, but once you evaluate it, how do you kind of use both of these? I guess just when you're doing a general thing.
Okay, so let me just copy it. So I presume here, for instance, no, not here.
It'll be the bit underneath when you fit it and then evaluate model.
Yeah, okay, I need to. I mean, but the loss is, what is the question? Because I mean, you can compute the loss for the model, the fitted model, and the new test data, right?
I guess it's just more like in applications, which is more useful. Like how do you kind of use both of them?
Oh,
once you evaluate and you've got a loss and an accuracy, how do you kind of, which one do you use to compare? And I guess,
I would generally look at the accuracy, because, so I mean, when you're saying compare, in what circumstances are you thinking of?
I guess comparing different models.
Yeah, so then the different models you may have. Okay. The different models may even have different loss functions, right? And so in that case, what is the meaning of comparing these?
Yeah, that makes sense. So is it like basically that the loss that gets outputted in R when you evaluate isn't really that useful?
Yeah, I mean, maybe, so you would only have, I mean, sometimes the loss function has a meaning in that, it tells you something about the variance, right? It tells you something about, okay, not good. It tells you something about, the scale of accuracy that you achieved, right? But I would take accuracy as the quantity to be comparing 100%, because I mean it could also be, let's see. Yeah, so it may make sense to compare loss function values when you have the same loss function, right? So then there you could say, well, why not compare them? But then you can compare them, but and you can check that one is better relative to the other. But in absolute terms, how do you make a statement? While with accuracy, you have both a relative comparison between the two and also an absolute comparison, because you think that accuracy of 80 is not good, while accuracy of 99 is good, right?
Yeah, thanks.
Yeah, no problem. All right, more questions?
Hi, Dr. Coco.
Yeah.
Could you explain when an epoch is taking place? I'm thinking about sort of the visualization on R. The accuracy goes up to hit its last value, and that's the accuracy value for the epoch. What's happening that the accuracy value is sort of going up as the training happens over that epoch?
So are you saying that for every single epoch that happens, that it improves within the epoch?
I'm not necessarily sure if it sort of improves monotonically, but it certainly seems to go from 0 to whatever value it ends up at.
I mean, that would make sense, I guess, right? Because you're using all of the data points to, because you're getting more and more information to sort of walk around the space, to explore the space, right? That's assuming that you chose the learning rate correctly, right? Because then, I mean, I'm sure there are cases in which that's not true. So I guess this has to do with the early stopping of the algorithm, because if we don't wait a lot, then, if we just have a few epochs, then basically you're going to be, generally speaking, improving in the I don't want to say long term, but generally improving as you train. And an epoch is a use of all of the data points, so you would expect that to give you better performance than if you used just a few data points, right?
Yeah, that makes sense.
I mean, I'm not giving you a very definitive answer, but it's just purely intuition, I would guess.
That's helpful. Thank you.
No problem.
I'd just like to share with everyone that I haven't got the packages working. So if you're in this boat too.
You didn't get the packages loaded?
Yeah, but that's fine. I'm battling away.
So that's the issue that I was mentioning, I guess, here.
Yeah, it turns out like using a Linux dual boot is kind of harder than it sounds.
Yeah.
That's fine. Don't worry about me. I just thought I'd share that with everyone.
I had it too, and I just shut down R and boot it, launch it again, and it worked. So maybe you just should try again.
Yeah, I think the best solution is either, it's probably to try it out for a couple of hours, and if it doesn't work, then change computer, literally. Because I seem to remember seem to remember spending quite a lot of time trying to fix that, and I couldn't see how to make it work in some computers. Although that's not to say that I'm very good at this, fixing computer science issues or programming issues.
Hi, regarding the theoretical section about the pitfalls in training neural networks via looking at the back propagation formulas, I was wondering if you could just talk through that section. It makes sense, but I thought it'd be useful to hear you just go through it and like link the intuitions between the mathematical expressions.
So you mean sort of give a bit more details about these three?
Yeah, if that's okay.
Yeah, I mean, so there are many pitfalls that different activation functions can have, right? And you could be training the network with something that is not SGD, and so then you would have to understand, the particularities of those. But when you're doing SGD, you're only computing the gradient, and it turns out that to compute the gradient, one can do that sequentially, which is generally cheap. And this is the case with neural networks, feed-forward neural networks. And, if we think of when you try to propagate from the beginning of the data, right? So from the covariates to the labels, then you're sort of saying, well, I have my data, I have these parameters beta, I take the linear combination, then I map it through a nonlinear function, then I get a new value, and I do the same operation again and again for every layer. So you're doing this sequentially, and then you get to the end. And now that's all fine. But if you do that, then you go to the labels and full stop, right? You're not really using the labels from the data. And so if you were to train the algorithm, again, we go to SGD, and with SGD, we need the gradient, and the gradient sort of exploits that forward pass to then make it a backward pass, in which we're also going to take account of the label of the data, right? And that's key, actually, so that we train it, right? So it's very nice, I think, to see how the label of the data is actually changing the values of the parameters of the forward pass. Right? And the precise way in which that happens is here. I think the derivations are purely just chain rule, and you have to sit down at home and just do them, basically. So it's just a matter of, so the Ri, and I was just thinking that Ri may not have been defined. So Ri, but you can imagine what it is. So let's see, where is this? Yeah, so R is this guy, which is just the average of the, well, not even the average, but I mean, in stochastic gradient descent, we assume that the F is an average of other Fi's. And so what we can imagine is that we have an average here. So 1 over n here. And so we multiply the capital L by n. And then each of those guys, so the n, small n, times the loss function for the ith data point is the Ri. Okay, so I hope that was clear anyway. And and so if we go here, well, the derivative with respect to beta, if we think of Ri as being, a function of a loss, and so it is a function of a loss, and the loss is basically at the highest level in the hierarchy, then it's better to differentiate rather than with respect to beta, to do it with something that is intermediate, and that's the next guy in the hierarchy above this beta is the S. Yeah, it's a linear combination of these guys, and so you can differentiate with respect to that, and then the S with respect to the beta. So you get that X out of from that derivation, and then you have this derivative that you can check that it gives you this, except for in the last layer where you get this. Yeah, and in this last layer is where we are really accounting for the, as I said, for the label of the ith data point, right? And that's exactly how we will then, once we arrive at the last layer, compute this delta, these deltas from the last layer that we can then sort of propagate back the influence of the label of that data point in such a way that it will be accounted for in every single update of the parameters, right? Because this will give us the update of the parameters. Yeah. Okay. And then given that, we now have very explicit expressions about the updates, and some common pitfalls are the three that I include here. And I think the first and the third are probably just the most immediate to see. Saturation is a very common issue, which is actually, if I remember correctly, let's see. If I remember correctly, it is saturation that happens here. Let me just check. Okay, now so vanishing gradient. Yeah. Yes, because that's the one. Because then we change the. Yeah. Okay. Anyway, so then. So what you can conclude from these things is that, as soon as this guy is 0, or as soon as, all of these guys are 0 or something of that kind, then you're going to have zeros in the updates. And of course, that will not make you move. And that's exactly the kind of issues that we see in practice. So it's just that if the parameter doesn't get updated, then that means that either it is at a minimum, or that is just basically something is not working properly. Yeah, and these are issues with not working properly, as we see, because we even see this at the very beginning of the training, right? So when is this guy 0? Well, it can be 0 for large values of S, for instance, absolute value in the sigmoid, or when we go to the left side of the ReLU activation function. And in such cases, because it is being 0 already, then even if you go through another pass and so on, the updates will be so small that it will essentially not come out of that region. And in the ReLU setting, this has a name in itself. And so, so you don't want to have very large values. That's one of the learnings that you take from saturation. And so you would think, so let's start then with all the zeros, all the betas being 0, and that has its own problems. So essentially what one concludes is that it's just a bit better to take small values, but randomly and around 0. Yeah. And so what are the issues that you can have? Well, the issues that you can have, so if you choose them, if you choose them all to be 0, then there are at least 2 options, right? Depending on the value of the activation functions, which of course, one could be a bit more precise here with the H's, but yeah, generally speaking, so this is actually, so this can apply for each layer, separately. So it's fine as it is. But if the value is 0, then what we know is that the image of the linear combinations, when these linear combinations are 0, is going to be 0. Yeah. And so if we take all of the parameters beta to be 0, of course, regardless of the covariates that we fed it with, we're going to get that the guys in the first hidden layer are going to be 0 because the linear combinations are 0 and they're mapped by a function that takes you 0 to 0. And so then you get zeros in the first layer, and by the same reasoning, you get zeros everywhere, basically. Yeah. And if you get zeros everywhere, well, then you're dead, basically, because these guys are always going to have a zero. Yeah. So that's the issue with these activation functions. And there is a comment here, except perhaps the bias weights for the output layer. You should think, and there is also a comment here later. So maybe let me give you intuition for these two comments. I mean, essentially everything that happens in the hidden layers is a bit away from the data, right? So if we expect any changes to happen as a result of the data, those would be, at the end or at the beginning of the network. And this is exactly what happens here. And now, why are the bias weights for the output layer maybe changed? Well, so let's go to the update of those. So the bias node of the output layer would be k equals 0 and h equal h plus 1. And so k equal 0, what will give us here is an x0 of the previous layer, but the x0 of the previous layer, we took it to be 1, if you remember, by convention. And so basically what we need to argue is that the delta for the h plus 1 layer is non-zero. And you can check that due to having this data here, you will get values which are not necessarily zero here. Yeah. Now, of course, it's key that we're in a bias node, because if this k were not 0, but rather a different value, then it would be 0 from the previous argument. Yeah. And so we'd be killing it. Okay. So it's a matter of sort of reasoning like that. So I've given you the answers. Now it's a question of getting to argue them. And then, yeah, we have the other option. So the other option, what again it does is to change the value of the x's, right, that receive the zeros. So at the beginning, you will have some data. You have betas that are 0. Take a linear combination that gives you 0. But you map it through a function that doesn't take 0 to 0, but it takes it to a different value. And then that value, when we take the linear combination, will be 0 again. So again and again, you repeat the operation up until the end. And then once you get to the end, you compute this guy. And you know that now these guys are not going to be 0. So that's good news. And this guy, let me just think. Yeah, so for these guys, you would need to compute. Oh, no. Okay, wait. So we have the betas here, which are 0. We inherit them to be 0. And let me just see what I'm trying to get to. And if this guy is for the sigma, it will change, but will be equal in each layer. Except okay, yes. Okay, so these are 0. But the ones that may not be 0, actually, are the ones in the last layer. So the ones of the h plus 1 layer. Those may not be 0. And then you go down the layers and you get zeros from here. And so you go back to the sort of origin and you start doing exactly the same thing. But now the last time, the last layer, the output layer, will now give you betas that are not 0. And so that will propagate back. And so little by little, you start filling up the betas with non-zero parameters. And these are going to be the same for every element in a given. So the k will not change the value because the k was coming precisely from the same values. There's deltas. The deltas only depend on the data point and the j and the layer, of course. And then these k's, these x's are going to stay basically constant. And now it says except for the first hidden layer, and that's of course because the x's were not constant in those. Yeah. So they are data and they contain different values, and you can check this in at a practical level. And then the last thing is this vanishing gradients, which is again looking at this derivative. And yeah, of course, it's the issue that we had here. And it's just a problem of multiplying small numbers by themselves. Yeah? It's just the power of numbers that are small that will essentially give you very small values. And so what it means is that if you have an accumulation of layers whose activation gradients have gradients that are, the activation functions have gradients that are very small, then this will just give you a product of things that is very small. And this is because these deltas come in, in this way, right? And that is it, I think. Yeah, and this is why we choose ReLU here. So of course, we had an issue here with ReLU, but this issue is completely resolved by taking these random starts and then trying to avoid saturation by taking precisely small values. So this sort of sorts out saturation at the beginning of training, and then this avoids the issue with ReLU, and ReLU is better than sigmoid in the vanishing gradient. So it means when you add in more than 2 layers, hidden layers, and so the take-home message is probably ReLU is a good activation function to take rather than sigmoid. Okay, I think there's a question in chat. You can also use Kaggle, which has all the libraries. Yeah, that's another option.
Oh, could I ask a question following on from?
Yeah.
At the very end of the practical, before the non-examinable section, we have this problem with the weights not being updated. And the reason was because the first few pixels are constantly white in all of the input images. And so we get the same sort of thing. Could we, as in the previous practical, delete all of the pixels that have the same value across all of the images before we train the neural net? Or is this generally not done in neural networks?
Yeah, that's generally done, yes. Yeah, okay. I think, yeah, practicals in many occasions have an illustrative purpose, so that you've seen these things rather than them being exactly in the optimal way in which one would do it.
Sure. Okay, cool. Yes, it makes sense.
Yeah, sure.
Cool. Thank you.
So I think, let's see. Well, I guess it's not done here. I don't remember it being done here. Yeah, the issue with that. So, I mean, if you want to do it with the convolutional networks, then you've got to be careful, because
yes,
you want to keep geometries, and so you don't want to take out a given pixel and then have a hole in there.
Yeah.
Or if you do, you've got to somehow tell the network to do something about it, which is certainly not an immediate instruction to give. So the option is just removing whole columns, right?
Yeah.
Yeah.
Or if, say, the margin is completely white, then you could get rid of the top row of pixels instead, and you might still be fine for CNNs. Right?
Say it again.
If the top entire row of pixels was entirely white for all of them, then you could just get rid of those.
Yeah, exactly.
Okay, cool. That clears things up. Thank you.
No problem.
No, I had another question, and I'm not sure if it's already been asked, if that's okay.
That's okay.
How do you calibrate the learning rate in general?
Yeah, that's quite an art, actually. So there are automated schemes for that. But otherwise, so I mean, this is the rule, yeah. This is the rule that gives you theoretical guarantees, which is saying that they should be small and they should be decreasing, but not very fast. What that means in practice is nothing, basically. But again, if you're worried about that, I mean, there isn't. I mean, there is. You could, of course, be, trying out different ideas and doing some cross-validation or doing some, or just checking the test error, basically. And but there are things that are being thought of, and these you can check in Keras, because there are more automated schemes for this. But the problem with automated schemes is that they're a bit too generalist many times. So you could be, for instance, looking at second derivatives, right, and trying to use that just in the same way the Newton-Raphson adapts to the shape. The problem here is that you just have an absolutely massive amount of parameters, and so there isn't much that you can do. And so there are some cheap approximations to second derivatives as well that you can try to use. And I think that's pretty much, I mean, what these automatic methods are based on, basically.
I see. Because when I looked at the condition, I thought perhaps you would use the harmonic series or something. But I guess it's just not.
You could do, but that's theory. I mean, that's just for the theory. I don't think it gives you a good idea of what to do in practice.
I see. That makes sense.
Because I mean, that's also under some conditions, right? Which generally you cannot check.
Yeah. And just to clarify one more point, with Newton-Raphson, I've always read it to be something to do a bit like gradient descent, where you consider the first derivative only. So is there a different, like a version of Newton-Raphson which uses the second derivatives as in our course?
Well, but think of Newton-Raphson as a method to find the zeros, right? It's not really gradient descent. So gradient descent is trying to minimize or maximize. Newton-Raphson is trying to find the zero in a function. And it does so by looking at the derivative of the function.
Yep.
That is true. But then if you look at it for the purpose that we are using it, which is optimizing, then really what you are applying Newton-Raphson to is the derivative already. And so you are using the second derivatives. And if you write out things carefully, you will see that essentially what that is doing is using the second derivative to choose the step size, or to adapt the step size to the curvature of the function at each step.
Okay, because I always had known Newton-Raphson to expand to the first order and use the first order derivative only.
But again, I mean, when you say first derivative, are you thinking of the first derivative of the function whose zero you're trying to find?
Yeah.
Yeah, but then that's the gradient for the
right. Yeah,
function that we are using. Yeah.
Sure. Cool. That's cleared up everything. Thank you.
Sure. No problem. I mean, ideally you would use second derivatives to have a more informed step size. But again, I mean, we already spoke about this in logistic classification, that it could be too costly. And this was when the number of labels and number of parameters was too high. And so, of course, in neural networks, this is insane. So it's just not possible to do it unless you do it through some cheap approximations, in which you're, of course, paying some price for having a bit more information than you would otherwise.
Yeah, I have a question. What is the typical size for the number of parameters for model, and also the typical ratio from parameter size to sample size?
I really don't think there is a typical value. So I mean, we've seen here different examples, right? In which, what did we have at the very beginning? So yeah, so we started with 72, and then you see that as soon as you add a layer, things really become serious, and you get a serious amount of parameters. And so here, for instance, we had, this 200,000, which is a ridiculous amount of parameters. I would say if you're trying to find such an idea or such a guide, it will probably depend on the application. So every application may need more or less. So for instance, in imaging, you will have a generally quite high number of parameters. But then on the other hand, you may also have quite a lot of data. I don't think there is, I'm not aware of any rule of thumb, to be honest, with these things. I think beginning with 3, 4, 5 layers and checking out how that works, and then trying to adapt from that and trying out a few things, that's just the usual thing in complicated applications. Because I mean, using 3 layers, we've already seen that can give you several thousand variables. So if you have 3 data points to train with, or 10 or 20, then maybe that's not the best start that you can make. But assuming you have a modern, assuming you have a different scale of data than that, then it's not a bad idea to start with a couple of layers and take it from there. But I don't think there is a definitive answer as the number of parameters, because I mean you can also use regularization methodologies, right? And if you do, then maybe the meaning of if this regularization procedure is very, very harsh, then maybe you can start with a lot of parameters, even in a problem which you wouldn't expect to be using a lot of parameters, and the other way around, right? If you propose something with not that many parameters and you don't regularize, then actually that may be okay in itself. So no, I don't think there is a clear answer. But we are talking about thousands of parameters, generally speaking.
Okay, and so maybe I guess there's no rule of thumb neither for choosing the architecture of the network.
Yeah, so the architecture is a bit different. The architecture does have a lot more meaning, generally speaking, than the number of parameters per se. And you see this precisely in the non-examinable bit, that if you change the architecture, so if you, rather than using vectors for each layer, you use matrices, and then the activation rules, they, well, not the activation rules, but the zeros in the parameters are designed in a very particular way, then actually you will be extracting information that is adapted to the application. So in this case, it is extracting information about images in a way that works much better than if you had flattened out the matrix and using a feed-forward network. So the architecture, I think that does change depending on applications. Yeah? And it's even the case that every single layer will have a different meaning. So there are applications in which this happens, including imaging, as we see here. And this is the last comment, basically. And then the activation functions themselves, those are important as well, because there are pitfalls like the ones that I mentioned here. And so it matters as well which ones you take. But again, this is very much application driven or application dependent. But keep in mind that architecture is definitely one that is important in building the models.
Okay, thanks.
No problem. Okay, so if there are no more further questions, then we'll stop here. And I'll see you on Wednesday for yet another classifier. So the last one of the course, which is nearest neighbors. And then after that, we'll begin with time series. So you have a minute to shout out if you have a question that is like an offline question.
I was just wondering, do you find yourself using neural networks often?
Well, I don't.
What are your opinions?
Well, I don't. My research doesn't concern using any of these algorithms, actually, because I do non-parametric stats. When it comes to, for instance, a few organizations that I'm helping out, yes, I mean, the answer is yes. They do use neural networks all the time. In fact, I would say it's a bit too much of a rule of thumb to start with a neural network and not think about the problem, rather than the old way of being a bit more careful in the model design, and then if nothing works, then resorting to these things. Yeah, I mean, I think if they are trained appropriately, and by trained I mean if you design the architecture carefully and number of layers and everything is designed very carefully, then they can be very, very powerful. But as you can see here, I mean, there are a lot of these are extremely complicated models in terms of trying to understand what is going on, right? And so this is why this practical focuses a bit more on that than on any other aspects. So it's more about changing the activations. It's more about checking these things, what can happen, so that you also have a an idea of how to check the different things. But when it comes to using it, then again, that's very, very application dependent. So in many occasions, it's really a lot about the starting matrix. So the first beta that you choose. So because you want to fall on the right place of the space. So, you have an architecture that is generally working. I mean, so just to yet again answer the question from before, there are some architectures that are, the baselines, so to say, for a number of applications. And so then it's a matter of tweaking them. And another very important thing is just choosing the starting matrix well. Yeah, the parameters that you're going to begin with in the stochastic gradient descent. Yeah. So in every application you will have to think about those things. So it is very much of an art, yeah. And you can have a paper with a few pages that is a few pages long, in which you essentially just chose the right things to give you the right answers. This happens with neural networks, or it used to happen at least.